Hello everyone, welcome to the video. Today we are going to discuss the problem longest increasing subsequence. In this problem, we are given an array of integers and we have to find a subsequence which has all the elements in strictly increasing order and its length is maximum possible in this array. In the past video, we solved this problem using the dynamic programming approach. In this video, we will be solving this problem using the binary search approach. We will go through the thinking process, we will write the algorithm, and finally also see the working code for this question. So before we start, if you are new to this channel, please don't forget to subscribe and press the bell icon. Let's start. To begin with, let us first note down the key things given in the question. We are given an array of integers and we have to return the length of the longest increasing subsequence. What does that mean? Let us understand one by one. So subsequence means we have to return some elements of this array, but those elements have to be in order. Then increasing subsequence means every element of that subsequence should be greater than the previous element. Then the question also mentions that it should be strictly increasing subsequence. That means every element of that subsequence should be greater than the previous element. Even equal won't do. That element cannot even be equal to the previous element. Now coming to the last term, longest. Now we will have many subsequences that satisfy this condition, but we have to return the length of the subsequence which is longest among those. So if we consider the example here, this is an array that was given to us as input. Then here answer will be 3. Why? Because 5, 7 and 9 form a subsequence which is strictly increasing and it is the longest possible in this array. So if we consider our solution as a black box, we are getting as input an array and its size as input, and we have to return the length of the longest increasing subsequence as output. So what will our function signature look like? Our function signature will look something like this. Before jumping to the solution, let us try to see how a common student will think about this. So consider this as our example array. Our aim is to find the longest increasing subsequence in this example array, the length of the longest increasing subsequence. So let us consider each of these elements one by one and see how does the longest increasing subsequence develop as we move forward in the array. So consider the first element here. What if array had only this element? Then what would have been the longest increasing subsequence? It will be 1. Then we will come to the second element. Now let us say we had only 1 and 7 in the array. Then what would have been the longest increasing subsequence? It will be 1 and 7. Now as we encounter 8, the longest increasing subsequence will be 1, 7 and 8. So far, the length of the longest increasing subsequence is the length of this array, 3. But now what happens when we encounter 4? Now when we see 4, 4 cannot become part of this subsequence. Why? Because then it won't be an increasing subsequence. But 1 and 4 can be another subsequence that we can track. The length of the LIS still is 3 because of the 178. 1, 4 does not become LIS, but we still have to track it. Why? Because as we encounter further elements in the array, it is possible that the length of this array becomes greater than the length of this array, and therefore our LIS becomes this. Why is it possible? Because consider these two arrays at this position. Here 7 is greater than 4. So for an increasing subsequence, the scope of the elements that can come in this array are greater than 7. While for increasing subsequence, the scope of the elements that can come further in this array are greater than 4. So this has more scope and hence it can actually get ahead than this array. So we cannot ignore this subsequence 1 and 4. We will have to track it. So in a way, these two are our candidate longest increasing subsequence. Any of these can become are longest increasing subsequences. So here comes our first observation, that as we move forward through the array, we are creating candidate LIS. And then finally, one of them will be our final LIS, which will be our answer. Now let us see what are we essentially doing with every element as we pick it. We are basically forming LIS ending at that element. First of all, we picked 1. At that time, LIS ending at 1 was just 1 and its length was 1. Then we picked 7. At that time, LIS ending at 7 was 1, 7 and its length was 2. Then we picked 8. At that time, LIS ending at 8 was 178 and its length was 3. Then we picked 4. At that time, LIS ending at 4 was 1, 4 and its length was 2. But since so far our maximum length that we encountered was 3, therefore till this point our length of the longest increasing subsequence was 3. This is the very similar to the approach that we used in our dynamic programming as well, where we calculated LIS ending at every element and then we took the maximum of it. So here comes our second observation, that for every element that we are picking, we are basically forming LIS ending at that element. Now let's move forward from 4. So the next element will be 5. Now 5 cannot be part of this subsequence. Why? Because then it won't be an increasing subsequence. But it can be part of this subsequence as 1, 4, 5. Therefore, LIS ending at 5 is 1, 4, 5 and its length is 3. Now what do we have? We have two candidate LIS. Both have length 3. One ends at 8 and one ends at 5. Now which of these is superior? Meaning which of these is better for our answer? It will be 1, 4, 5. Why? Because now as few elements are left in the array to be seen, 178 can never be our answer. Why do we say that? Because any element that can help grow this subsequence has to be greater than 8. And if we encounter any element greater than 8 among the further elements of that array, that will automatically become part of this subsequence. Because since that element is greater than 8, it will obviously be greater than 5. But there may be some elements like 6 and 7 which can become part of this subsequence but not a part of this subsequence. Therefore, we can say that if we have to choose among these two subsequences, our final answer will always lie in this subsequence. And hence we can say that this subsequence is superior than the first one. So here comes our third observation, that if the two candidate LIS are of same length, then for us the one with the smaller last element is superior. Now let's move forward in the array. So now we encounter element 6. Now element 6 can become part of this subsequence. So the LIS ending at 6 is 1, 4, 5, 6 and the length of LIS ending at 6 is 4. And this is also now our final LIS till this element, because the length of this array is greater than this now. Now let's see what happens with -1. Now -1 cannot become part of any of these subsequences, but it can actually start its own increasing subsequence because we don't know what will be further elements that come in this array. So the LIS ending at -1 is just -1. Now let's see what happens with 9. Now 9 is greater than all of these last elements. So 9 can become part of all of these. So the candidate LIS ending at 9 can be this, this or this. Now the array is done and we have 3 candidate LIS. So what will be our final answer? Our final answer will be the middle LIS. Why? Because its length is maximum and we are looking for longest LIS. So what essentially we have done here is that we have picked every element and we have tried to form the best LIS ending at that element. And then once we were done with all the elements, we returned the maximum length of the LIS that we could see so far. What will be the time complexity and space complexity of this solution? The time complexity will be big O of n square because we are going through all the n elements, and for every element we may have to go back all the way to figure out what should be the appropriate position to place that element. This approach is similar to what we saw in our dynamic programming approach in our previous video. To fill any LIS ending at a position I, we were looking for a J where AJ was less than AI and J was also less than AI, but LIS ending at J was maximum among all the LIS ending at all J's that are eligible. Therefore, time complexity is big O of n square, and since we have to maintain multiple arrays that can also be in the order of n, space complexity also goes to order of n square. While our dynamic programming solution had space complexity of big O of n, so this solution so far in a way is worse than our dynamic programming solution. So let's see how can we optimize this. We can see that here we kept track of all the elements that were forming a particular LIS. But we only need the length, we only need to keep track of length. So maybe there is some scope of optimization here. So let us see if instead of maintaining these multiple arrays, we can try to do this in a single array. Here we needed an extra array when we encountered this element 4. So let us go a step back and let's say that we have now seen till 1, 7 and 8, and we are maintaining this in 1, 7 and 8, this one array. Now let's try to give meaning to this array. Here we can say that we have an LIS of length 1 that ends at 1. Here we can say that we have an LIS that ends at 7 and whose length is 2. Here we can say that we have an LIS that ends at 8 and whose length is 3. And the length of this overall array denotes the LIS, length of the LIS that we are looking for. In a way, the position of the element is also denoting the length of the LIS ending at that element. For example, 8 here is at third position. So this third position is also denoting that the length of the LIS ending at 8 is 3. Now let's say we encounter 4. Now LIS ending at 4 will be 1, 4, which is of length 2. But we already have a length 2 LIS, 1, 7. But which one will be superior among the two, 1, 4 or 1, 7? 1, 4 will be superior because the last element of 1, 4 is smaller than the last element of 1, 7. So let's say that I remove this 7 and put 4 instead. Now let us see what does this array denote. For the array has now 1, 4, 8. Now the first element denotes that there is a best LIS of length 1, which ends at 1. There is this best LIS of length 2, which ends at 4. Then there is best LIS of length 3, which ends at 8. Since we have the LIS till length 3, our answer finally is 3 so far. But what we have done here is, by removing 7 and placing 4, that we don't care about the LIS ending at 7, because there is a superior LIS that ends at 4 and is of same length. So what essentially we are doing here is that every element of this array is maintaining what is the best LIS for that length. And that length, by that length we mean the position of that element. So this denotes that the best LIS for length 1 is the one that ends at 1. The best LIS for length 2 is the one that ends at 4. The best LIS of length 3 is the one that ends at 8. Now we encounter the next element 5. Now what do we do with 5? LIS ending at 5 will be 1 comma 4 comma 5 whose length is 3, which is superior than our current length 3 LIS. So we can remove 8 and replace it by 5. Now our array has elements 1, 4, 5. So we are maintaining this property in this array, and as we maintain this property, the final length of this array will be our answer, because the final length will denote that there is some LIS of this length that ends at a particular element. Now we encounter 6. Now with 6, the LIS ending at 6 becomes 1, 4, 5 and 6, which is of length 4 that we don't have so far in the array. So we add here 6. Now this array has elements 1, 4, 5, 6, and this denotes that the best LIS of length 4 is the one that ends at 6. And the length of the LIS that we are looking for so far is 4, which is the length of this array. Now we encounter -1. Now with -1, it is smaller than all these elements. So the LIS ending at -1 will just be -1, which is of length 1. But our current length 1 LIS is 1 only, is the one that ends at 1. Therefore, we will replace 1 with -1 now. So now our array has elements -1, 4, 5, 6. But what does this denote? This denotes that the best LIS of length 1 is the one that ends at -1. And now we come to the element 9. Now element 9 is greater than all of these. So LIS ending at 9 can be equal to LIS ending at 6 plus 1. And LIS ending at 6 is of length 4. So 9 can be added at the end of this array. Now we are done with all of our input array. And since this array has 5 elements, our final answer is 5. That the length of the longest increasing subsequence that we were looking for is 5. But it is very important to note that these elements do not form any LIS. This array is not storing any LIS. It is important to understand that what does this array represent. This array represents that for every length, what is the best possible LIS. For the first element, we can say that for length 1, the best possible LIS is the one that ends at -1. For length 2, the best possible LIS is one that ends at 4. For length 3, the best possible LIS is one that ends at 5. For length 4, the best possible LIS is one that ends at 6. For length 5, the best possible LIS is one that ends at 9. So it is representing every LIS by the last element of that LIS. And since there is at least one LIS of length 5, our answer becomes 5. So with this solution, our space complexity got reduced to big O of n because now we are using only one array. But our time complexity is still big O of n square because we are dealing with every element of this array, and for every element we are looking for first element that is smaller than it when we travel from right to left in this array. Why do we look for the first element smaller than it when we travel from right to left in this array? Because that element will denote the longest possible LIS that ends at any of these elements prior to our current element. Consider how did we place 4. When we were placing 4, we already had 1, 7 and 8. So we traveled from right to left, 8, 7 and then 1. When we found 1, we stopped and we put 4 right next to 1. Why did we put 4 right next to 1? Because among all the elements that lie prior to 4, the LIS ending at 1 was the longest possible and where the element was smaller than 4. Similarly for 9, when we were placing 9, we encountered that hey 6 is smaller than 9 and LIS ending at 6 is the greatest. Therefore, our time complexity is big O of n square, as for every element we may have to travel n steps again. But we can note very interesting property here. The interesting property is that this array will always be sorted. it will never happen that an element smaller than a previous element is placed in the right. Because for every element, we are first finding the element that is just smaller than it, and then we are placing the element right next to it. So this array is always sorted. So can we use this property to optimize the time of placing every element in this array? Basically what we are looking for is, we are looking for an element or a position that is just smaller than the value that we are looking for. We can use binary search. Binary search is not just used to find the presence or absence of an element. In a sorted array, it can also be used to find the right position at which that element should be present, if at all we want to place it in that array. So with this, our time of placing an individual element will come down to big O of log n instead of big O of n. So our time complexity will become big O of n log n. So our algorithm is pretty simple. We first declare this new array, then we iterate over our input array. From our input array, we pick our element one by one. And in every iteration, we find the most appropriate position in the new array for that element to be placed. We can find that position using the binary search. And then we place that element there. And as we complete this for all the elements in our input array, we can return that whatever is the length of the new array, wherever we had placed our last element. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So first of all, we declare a new list, which is best LIS for every length. We are using a list here instead of an array because we don't know the exact length of that array that we will be returning. So we declare this new list. First of all, we add the first element in that list, because till we have seen only the first element, the best LIS for length 1 will be the one that ends at the first element. Then we iterate over our input array, and for every element in that input array, we check if that element is greater than the last element of the list that we are constructing. If it is greater than the last element of the list, we can simply add that to the back of the list. But if it is smaller, then we have to find the appropriate position for this element. To find the appropriate position, we use this built-in method collections.binarySearch, and we use that on our list, and we have this current element's value, which is our key for the binary search. Now, if this was found in this list, it would return the index. But if it was not found in this list, this method returns a negative answer. And from that negative answer, we can derive what should be the appropriate position at which it should have been inserted. So we use that and we substitute the element at that position with our current element. This then denotes that the length of the LIS, that the best LIS for that particular length at that index is the one that ends at this element. Once we are done iterating for all of the elements, we finally return the length of the list that we have formed. We return the size. So this is the code for longest increasing subsequence using binary search solution, and its time complexity is big O of n log n, which is better than our dynamic programming solution. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also, let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.